If we want to find the average of a group of numbers, we add up all of those numbers together and then divide by the number of numbers. We can do something similar if we want to describe the average spatial location. Now, instead of summating as in 1 plus 2 plus 3, etc., we are going to be integrating, meaning that we're going to take a very large number of these points, add them together, and then divide by the number of points. In calculus terms, this right here, the position of each individual point, can be thought of as its value when finding the average. And each point has a value of either dV if we're talking about volume, or dA if we're talking about area, or dx if we're talking about length. But we do the weighted summation of all of those points up top. And then down here, this integration is finding the number of these volume points or the number of these area points. Now, when we do it like this, we are finding the average spatial location, otherwise known as the centroid of the object. We could do this for something else. We could be finding the center of mass, which is the location where that is the average, the mean of all the masses in the object. Center of mass is also sometimes known as the center of gravity, because if we take the distributed force that is gravity, because gravity is all points of matter acting on every other point of matter, the sum of all of those actions can be thought of as a single force acting at this center of mass. So we find its position in a similar way. X times dm, so x is the value and each piece of mass is 1 dm, divided by the total number of these dm's, or the integral of dm. Now, with center of mass, we can often write it in terms of integration with respect to v, or again area or length, by finding the density, by saying that dm, a small chunk of mass, is equal to the density times a small chunk of volume. Now, sometimes, especially when trying to find the average point of a line, if that line is curved, we might have trouble finding these individual equal chunks of mass. But what we can do, and this is, if you want an image, look in your text on page 469. But we can define a dl. dl is a small chunk of length. And if we know that that wire has some function y of x, then we can say that for a given change in dx, for a given change in the x coordinate, there is a total length to that chunk of wire. We can use the Pythagorean theorem right here. dl is equal to the square root of dx squared plus dy squared. We can use the chain rule to say that dy is equal to dy dx times dx. And then we can pull this dx squared out here, this dx squared out here, both of them outside the square root. So dl is equal to the square root of 1 plus dy dx squared dx. Now, all of this right here works if you have a single well-defined object. But sometimes you don't. Sometimes you have an object that has all sorts of boundary conditions and what have you. Sometimes it's easier to take an object and break it up into individual pieces, because combining the pieces and finding their centroid or center of mass, this also works for center of mass, is actually not that difficult. If you can break it up into a number of pieces that each have an easily found center of mass or centroid, then you can find the net center of mass or centroid by using this formula right here, where Vi is the volume of the ith piece, Xi is the position of the the center of mass or the centroid of the ith piece. So this sum divided by this sum should give you your new centroid or center of mass. Finally, it's not just volume and mass that we can find the average value of. We can find the average value of nearly any quantity you might want to talk about. One that is of particular concern to us in dealing with statics is to find the center of force. If force is not a point force, but it is distributed over an area or a volume, then we can use our centroid math where it's integral of the weighting function times d area or d volume or d length divided by d length to find its position. Now we have already been doing this with distributed forces that are distributed in just a single dimension. Those are those W functions. We could find their force, we could find their moment, and we could also find where they were located by taking the net moment dividing by the net force, integral of W dx over integral dx, or Wx dx divided by W dx. Now for a force distributed over a certain area, we often call this the pressure force, pressure being measured in units of force per unit of area. One you might be very familiar with is the PSI, pounds per square inch of air pressure. The metric unit for pressure is the Pascal, which stands for a Newton per square meter. Now, one interesting aspect about pressure, especially pressure from fluids, is that as you go deeper into a fluid, the pressure increases. And as long as the fluid is incompressible, like water is, that pressure relationship is a fairly constant. P is equal to P naught. This is called the gauge pressure, or this is the surface pressure, pardon me. P naught is the surface pressure, the pressure at the surface, plus rho. Rho is the density of the fluid. G, that's that Galilean gravitational constant, 9.8 newtons per kilogram. And D is how far below the surface you are.